96 data curation, 365 to 380 index, 499. Data acquisition/annotation, 377 to 380 data coverage, 369 to 371 data quality, 368 to 369 data quantity, 372 to 377 data processing, 396 to 403 data cleaning and filtering, 401 data formatting, 401 to 403 deduplicating data, 399 to 400 inspecting data, 397 to 399 data-centric view of AI, 364 DDR SDRAM, double data rate synchronous dynamic random access memory, 423 debugging, 226 decoding autoregressive decoding bottleneck, 428 to 433 decoupling from pre-filling, 442 in transformer architecture, 58 defensive prompt engineering jailbreaking and prompt injection, 238 to 243 automated attacks, 240 direct manual prompt hacking, 239 to 240 indirect prompt injection, 242 to 243 prompt attack defense, 248 to 251 model level defense, 248 prompt level defense, 249 system level defense, 250 degenerate feedback loops, 491 demonstration data, 81 dense retrievers, 258 dimensionality reduction, 400 direct manual prompt hacking, 239 to 240 direct preference optimization, DPO, 84 distillation, 312 base, 358 model distillation, 182. 395, 427 synthetic data and 382 domain-specific capability, 161 to 163 domain-specific task fine-tuning, 314 domain-specific training data models, 56 to 57 dot products, 61 double data rate synchronous dynamic random access memory, DDR SDRAM, 423 DPO, direct preference optimization, 84 DRAM, CPU memory, 423 drift detection, 471 dynamic batching, 441 dynamic features, 30 edit distance, 130 ELO, 151, 152, 346 embedding, 134 to 136 embedding algorithm, 133, 135 embedding model, 10 embedding based. Retrieval, 260 to 263 multimodal RAG and 273 embedding models, 134 engineering architecture, 449 to 474 AI pipeline orchestration, 472 to 474 monitoring and observability, 465 to 472 drift detection, 471 logs and traces, 469 to 470 metrics, 467 to 469 monitoring versus observability, 466 step 1, enhancing context, 450 step 2, putting in guardrails, 451 to 455 guardrail implementation, 455 input guardrails, 451 to 452 output guardrails, 453 to 454 step 3, adding model router and gateway, 456 to 460 gateway, 458 to 460 router, 456 to 457 step 4, reducing latency with caches, 460 to 463 exact caching, 461 semantic caching, 461 step 5, adding agent patterns, 463 engineering stack, 37 to 39 application development, 37 AI interface, 45 evaluation, 44 prompt engineering and context construction, 45 infrastructure, 37 milliliters engineering versus 40 to 44 model development, 37 entropy, 119 epochs, 360 error correction, 292 to 294 evaluation, 44 evaluation harnesses, 191 evaluation methodology, 113 to 157 AI as a judge, 136 to 148 AI systems. Evaluation, C systems evaluation, challenges, 152 to 155 500 index. Challenges of Foundation Model Evaluation, 114 to 117 Comparative Performance to Absolute Performance, 154 Lack of Standardization and Quality Control, 153 to 154 Scalability Bottlenecks, 152 Exact Evaluation, 125 to 136 Future, 155 Language Model for Computing Text Perplex ITY, 125 Language Modeling Metrics, 118 to 124 Rank Models with Comparative Evaluation, 148 to 156 Evaluation Pipeline Design, 200 to 208 Step 1, Creating an Evaluation Guideline, 202 to 203 Step 2, Evaluating all components in a system, 200 to 201 Creating scoring rubrics with examples, 202 Defining evaluation criteria, 202 Tying evaluation metrics to business metrics, 203 Step 3, Defining evaluation methods and data, 204 to 208 Annotating evaluation data, 205 to 207 Evaluating evaluation pipeline, 207 Iteration, 208 Selecting evaluation methods, 204 Evaluation-driven development, 160 to 161 Eviction policies, 461 Exact caching, 461 Exact evaluation, 125 to 136 Functional correctness, 126 to 127 Similarity measurements against reference data, 127 to 133 Exact matches, 129 Expectation setting, 32 Explicit feedback, 475 to 480 Factual consistency, 165 to 169, 202 Faithfulness, 164 Feature-based transfers, 104, 309 Feature-free transfers, 104 Federated learning, 348 Feedback design How to collect feedback, 485 to 489 When to collect feedback in the beginning, 481 When something bad happens, 481 When the model has low confidence, 483 to 485 Feed-forward computation, 447 Feed-forward layer, 62, 343 Few-shot learning, 213 to 215 Fine-tuning, 307 to 362 Defined, 42 Domain-specific tasks, 314 Fine-tuning and RAG, 316 to 319 Hyperparameters, 359 to 361 Batch size, 360 Learning rate, 359 Number of epochs, 360 Prompt loss rate, 361 Memory bottlenecks, 319 to 332 Backpropagation and trainable parameters, 320 to 322 Memory math, 322 to 324 Numerical representations, 325 to 328 Quantization, 328 to 332 Overview, 308 to 311 Structured outputs, 104 Tactics, 357 to 361 Techniques, 332 to 361 LoRa, 338 to 347 Model merging and multitask fine-tune ing, 347 to 357 Parameter efficient fine-tuning, 332 to 347 PFT techniques, 336 to 338 When to fine-tune, 311 to 319 Reasons not to fine-tune, 312 to 315 Reasons to fine-tune, 311 Flop, floating point operation, 70 Foundation models, 12, 49 to 112 Evaluation challenges, 114 to 117 Comparative performance to absolute performance, 154 Lack of standardization and quality control, 153 to 154 Scalability bottlenecks, 152 Inverse scaling, 71 Modeling, 58 to 77 Model architecture, 58 to 66 Model size, 67 to 77 Parameter versus hyperparameter, 74 Post-training, 78 to 88 Index 501. Preference fine-tuning, 83 to 88 Supervised fine-tuning, 80 to 83 Sampling, 88 to 111 Probabilistic nature of AI, 105 to 111 Sampling fundamentals, 88 to 90 Sampling strategies, 90 to 95 Structured outputs, 99 to 104 Test time compute, 96 to 99 training data, 50 to 57 domain-specific models, 56 to 57 multilingual models, 51 to 55 use cases, 16 to 28 coding, 20 to 22 conversational bots, 26 data organization, 27 education, 24 image and video production, 22 workflow automation, 28 writing, 22 to 24 full fine-tuning, 332 to 347 function calling, 288 to 290 fuzzy matching, 130 G gateways, 458 to 460 Gemini, 44, 99, 444, 483 generation capability, 163 to 172 global factual consistency, 165 goodput, 414 to 415 GPU on-chip SRAM, 423 ground truths, 127 grouped query attention, 436 guardrail implementation, 455 guardrails, 189, 251, 451 to 455 HH3 architecture, 66 hallucinations causes of, 107 to 111 defined, 105 and fine-tuning, 317 measurement, 166 metrics 467 superficial imitation and 393 hard attributes, 179 hashing, 400 hellaswag, 192 hierarchical. Navigable small world, HNSW, 263 high bandwidth memory, HBM, 423 hyperparameters, 74, 359 to 361 IIDF, inverse document frequency, 259 IF eval, 174 implicit feedback, 475 in context learning, 213 to 215 inconsistency, 106 to 107, 142 indexing chunking strategy and 268 to 269 defined, 256 with embedding-based retrieval, 261 retrieval systems and 266 indirect prompt injection, 242 to 243 inference APIs, 410 to 412 inference optimization, 43, 405 to 448 AI accelerators computational capabilities, 422 defined, 420 to 421 memory size and bandwidth, 422 to 424 power consumption, 424 to 425 case study from PyTorch, 439 inference overview computational bottlenecks, 407 to 410 online and batch inference APIs, 410 to 412 inference performance metrics, 412 to 419 latency, TTFT, and TPOT, 412 to 414 throughput/goodput, 414 to 415 utilization, MFU, and MBU, 416 to 419 inference service optimization, 440 to 447 batching, 440 decoupling prefill and decode, 442 parallelism, 444 to 447 prompt caching, 443 to 444 kV cache size calculation, 435. Memory bound versus bandwidth bound interference, 408 at model/hardware/service levels, 426 model optimization, 426 to 439 attention mechanism optimization, 433 to 436 autoregressive decoding bottleneck, 428 to 433 kernels and compilers, 437 to 440 model compression, 427 understanding, 406 to 425 AI accelerators, 419 to 425 502 index. Inference overview, 406 to 412 inference performance metrics, 412 to 419 inference performance metrics, 412 to 419 latency, TTFT, and TPOT, 412 to 414 throughput/goodput, 414 to 415 utilization, MFU, and MBU, 416 to 419 inference quantization, 329 to 331 inference service defined, 183 and inference optimization, 406 throughput/goodput, 414 to 415 inference service optimization, 440 to 447 decoupling prefill and decode, 442 parallelism, 444 to 447 prompt caching, 443 to 444 inference with reference, 430 INFOBench, 174. Information aggregation, 26 information extraction, 243 to 247 information retrieval optimization, 267 to 272 chunking strategy, 268 to 269 contextual retrieval, 271 to 272 query rewriting, 270 re-ranking, 269 instruction data synthesis, 388 to 391 instruction following capability, 172 to 177 instruction following criteria, 173 to 175 intent classifiers, 457 intertoken latency, ITL, 413 interface, AI, 45 internal knowledge, 301 inverse document frequency, IDF, 259 inverted file index, IVF, 263 iteration, 208J. Jailbreaking, 238 to 243 automated attacks, 240 direct manual prompt hacking, 239 to 240 indirect prompt injection, 242 to 243 Jamba architecture, 66 judges, CAI judges, KK nearest neighbors, KNN, 262 kernels, 436, 437 to 440 key vector, K, 60 key value, KV, cache, 433 to 436 key value vectors, 323 knowledge augmentation, 279 knowledge augmented verification, 167 KV cache, C key value cache, L lang chain, 232, 250, 303 language modeling metrics, 118 to 124 bits per byte, 121 bits per character, 121 cross. Entropy, 120 entropy, 119 perplexity, 121 perplexity interpretation and use cases, 122 to 124 language models, 2 to 6, 125 large language models, 8 to 12 AI product defensibility, 31 role of AI and humans in the application, 30 to 31 set expectations, 31 large multimodal model, LMM, 9 latency AI judges and 144 inference performance and 412 to 414 metrics, 33 reliability versus 455 layer stacking, 354 to 355 leaderboards, 152 to 154, 191 to 197 learning rate, 359 leniency bias, 490 lexical similarity, 130 to 131. Linear combination summing, 350 to 352 llama attention function, 62 data coverage, 370 data quality, 368 data quantity, 372 data synthesis, 387, 390 fine-tuning, 310 inference optimization, 439 inference quantization, 330 model distillation, 395 open source models, 182 prefer, 84 preference fine-tuning, 78 prompt template, 215 scaling law and 73 LLM as a judge, 136, see also AI as a judge, index 503. LMM, large multimodal model, 9 local factual consistency, 165 locality sensitive hashing, LSH, 263 logit vectors, 89 log probs, 93, 204 logs, 469 to 470 long-term memory, 301 loop tiling, 438 LoRa, low-rank adaptation, 338 to 347 configurations, 341 to 343 LoRa adapter service, 343 to 345 mechanism of operation, 340 quantized LoRa, QLoRa, 345 to 347 low-rank factorization, 340 LSH, locality-sensitive hashing, 263 Mamba architecture, 66 manual generation, 383 to 386 masked language models, for massive multitask language understanding, MMLU, 34, 192 matches, 150 MBU, model bandwidth utilization, 416 to 419 MCQs, multiple choice questions, 163 mean time to detection, MTTD, 466 mean time to response, MTTR, 466 memory, 300 to 304 internal knowledge, 301 long-term memory, 301 short-term memory, 301 memory bottlenecks, 319 to 332 bandwidth bound, 407 memory math, 322 to 324 memory needed for inference, 323 memory needed for training, 323 to 324 quantization, 328 to 332 inference quantization, 329 to 331 training. Quantization, 331 to 332 size and bandwidth, 422 to 424 memory math, 322 to 324 metrics, 467 to 469 correlations between, 208 for AI as a judge, 142 to 144 for generation capability, 163 for hallucination measurement, 166 inference performance metrics, 412 to 419 language modeling, see language modeling metrics, observability metrics, 466 reference-based versus reference-free, 127 tying evaluation metrics to business metrics, 203 usefulness thresholds, 33 MFU, model flops utilization, 416 to 419 milestone planning. 33 mixture of experts, models, 68, 354 milliliters engineering, AI engineering versus 39 to 46 MLP modules, 62 MMLU, massive multitask language understanding, 34, 192 model APIs, open source models versus, see open source models, model APIs versus, model architecture, 58 to 66, see also specific architectures, e. Transformer architecture, model bandwidth utilization, MBU, 416 to 419 model compression, for 27 model development, 37, 40 to 44 dataset engineering, 42 inference optimization, 43 to 44 modeling and training, 41 to 42 model distillation, 395 model flops utilization, MFU, 416 to 419 model inference, 34 model merging, 347 to 357 concatenation, 356 layer stacking, 354 to 355 summing, 350 to 354 model optimization, 426 to 439 attention mechanism optimization, 433 to 436 attention mechanism redesign, 435 kV cache size. Optimization, 436 write kernels for attention computation, 436 autoregressive decoding bottleneck, 428 to 433 inference with reference, 430 parallel decoding, 432 speculative decoding, 428 to 430 kernels and compilers, 437 to 440 model compression, for 27 model ranking, 148 to 156 model router, 456 to 460 model selection, 179 to 200 model build versus buy, 181 to 191 open source models versus model APIs, 183 to 191 504 index. Open source, open weight, and model licenses, 181 to 183 model selection workflow, 179 to 181 navigating public benchmarks, 191 to 197 benchmark selection and aggregation, 191 public leaderboards, 192 model size, 67 to 77 scaling bottlenecks, 75 to 77 scaling extrapolation, 74 scaling law, building compute optimal models, 72 to 74 model-centric AI, 364 model-level defense, 248 modeling, 58 to 77 model architecture, 58 to 66 model size, 67 to 77 mixture of experts, models, 354 monitoring, 226, 465 to 472 MTTD, mean time to detection, 466 MTTR, mean time to response, 466 multi-query attention, 435 multitask fine-tuning, 347 multilingual training data models, 51 to 55 multimodal models, 9 multiple choice questions, MCQs, 163 n-gram similarity, 131 natural language feedback, 476 to 479 complaints, 478 early termination, 476 error correction, 477 sentiment, 478 natural language generation, NLG, 163 to 172 natural language processing, NLP, 163 to 172 needle in a haystack, NIAH, test, 218 obscure data lineage, 395. Observability, 465 to 472 on-device deployment, 190 online inference APIs, 410 to 412 open clip, 56 open source licenses, 181 to 183 open source models, model APIs versus 183 to 191 API cost versus engineering cost, 188 control, access, and transparency, 189 data lineage and copyright, 185 data privacy, 184 functionality, 187 on-device deployment, 190 performance, 186 open weight models, 182 OpenAI batch APIs, 410 evaluation harnesses, 191 first GPT model, 8 instruction hierarchy for model-level defense, 248 model as a service, 14 natural language supervision, 10 open source APIs, 183 progression/distillation paths, 357 quality of updated models, 196 test time compute, 97 operator fusion, 438 optimization inference optimization, C inference optimization, of retrieval systems, 267 to 272 p pairwise comparison, 400 parallel decoding, 432 parallelism, 444 to 447 parallelization, 226, 438 parameter-efficient fine-tuning, 332 to 347 adapter-based/soft prompt techniques, 336 to 338 LoRa, 338 to 347. Configurations, 341 to 343 How it works, 340 LoRa adapter service, 343 to 345 quantized LoRa, 345 to 347 Pareto optimization, 177 partial fine-tuning, 333 passive fishing, 242 PEFT, C parameter efficient fine-tuning, perplexity, 121 to 124 perturbation, 385 pipeline orchestration, 472 to 474 monitoring and observability, 465 to 472 drift detection, 471 logs and traces, 469 to 470 metrics, 467 to 469 planning index, 505. Plan generation, 286 to 292 complex plans, 291 function calling, 288 to 290 granularity, 290 reflection and error correction, 292 to 294 pointwise evaluation, 84, 148 position bias, 491 post-processing, 102 post-training, 42, 78 to 88 preference fine-tuning, 83 to 88 supervised fine-tuning, 80 to 83 potential model collapse, 394 power consumption, 424 to 425 PPO, proximal policy optimization, 87 pre-training, 41 precision bits, 326 preference bias, 491 preference fine-tuning, 83 to 88, 309 preference models, 147. Prefilling, 60 prefilling, decoupling from decoding, 442 proactive features, 30 probabilistic nature of AI, 105 to 111 hallucination, 107 to 111 inconsistency, 106 to 107 probabilistic definition, 105 to 111 procedural generation, 383 to 386 product quantization, 263 prompt attacks, 235, 238 to 243 automated attacks, 240 defense against, 248 to 251 direct manual prompt hacking, 239 to 240 indirect prompt injection, 242 to 243 prompt caching, 443 to 444 prompt catalogs, 235 prompt engineering, 211 to 252 basics, 212 to 220 context length and context efficiency, 218 to 220 in context learning, zero shot and few shot, 213 to 215 best practices, 220 to 235 break complex tasks into simpler sub-tasks, 224 to 227 evaluating prompt engineering tools, 230 to 233 give the model time to think, 227 to 229 iterating on your prompts, 229 organize and version prompts, 233 to 235 provide sufficient context, 223 write clear and explicit instructions, 220 defensive engineering, 235 to 251 information extraction, 243 to 247 jailbreaking and prompt injection, 238 to 243 prompt attacks defense, 248 to 251 proprietary prompts and reverse prompt engineering, 236 to 238 defined, 45 restricting model knowledge to its context, 224 terminology ambiguity, prompt versus context, 214 prompt loss rate, 361 prompt optimization, 230 prompt versioning, 233 to 235 prompt level defense, 249 proprietary prompts, 236 to 238 proximal policy optimization, PPO, 87 public leaderboards, 192 QQAT, quantization-aware training, 331 QLORA, quantized LoRa, 345 to 347 QPS, queries per second, 266 quality control, 393 quantization, 328 to 332 inference quantization, 329 to 331 training quantization, 331 to 332 quantization-aware training, QAT, 331 quantized LoRa, QLORA, 345 to 347 queries per second, QPS, 266 query rewriting, 270 query vector, Q, 60R RAG, retrieval augmented generation, 253 to 275 fine-tuning and 316 to 319 RAG architecture, 256 RAG beyond texts, 273 to 275 multimodal RAG, 273 RAG with tabular data, 274 to 275 retrieval algorithms, 257 to 267 combining, 266 comparing, 264 to 266. Embedding-based retrieval, 260 to 263 term-based retrieval, 258 to 265 106 index. Retrieval optimization, 267 to 272 chunking strategy, 268 to 269 contextual retrieval, 271 to 272 query rewriting, 270 re-ranking, 269 random feedback, 491 range bits, 326 ranking, 129 rating algorithms, 151 reactive features, 30 recall, 266 recurrent neural networks, RNNs, 58 reference-based judges, 147 reference-based metrics, 127 reference-free metrics, 127 reflection, 292 to 294 regeneration, 479 reinforcement learning from human feedback, RLHF, 83 to 88 relevance, 164 reliability, latency versus, 455. Replica parallelism, 445 re-ranking, 269 restricted weight, 183 retrieval algorithms, 257 to 267 combining, 266 comparing, 264 to 266 embedding-based retrieval, 260 to 263 term-based retrieval, 258 to 260 retrieval optimization chunking strategy, 268 to 269 contextual retrieval, 271 to 272 query rewriting, 270 re-ranking, 269 retrieval augmented generation, CRAG, retrievers combining retrieval algorithms, 266 main functions, 256 multimodal RAG and 273 quality evaluation, 264 sparse versus dense, 258 reverse prompt engineering, 236 to 238 reward models, 84 to 87, 147 RLHF, reinforcement learning from human feedback, 83 to 88 RNNs, recurrent neural networks, 58 role LLM, 176 role-playing, 175 to 177 routers, 456 to 457 role-based data synthesis, 383 to 385 SS4 architecture, 66 safety, 170 to 172 safety, as evaluation criteria, 170 to 172 sampling, 88 to 111 probabilistic nature of AI, 105 to 111 sampling fundamentals, 88 to 90 sampling strategies, 90 to 95 strategies, 90 to 95 stopping condition, 95 temperature, 90 to 93 top K, 94 top P, 94 structured outputs, 99 to 104 test time compute, 96 to 99 scaling bottlenecks, 75 to 77, 152 scaling extrapolation, 74 scaling law, 72 to 74 scoring rubrics, 202 self-evaluation, 146 self-supervision language models, 6 to 8 self-verification, 167 semantic caching, 461 semantic similarity, 132 to 133 sequence parallelism, 447 sequential fine-tuning, 348 SFT, supervised fine-tuning, 78, 80 to 83, 309 short-term memory, 301 simulation, 385 simultaneous fine-tuning, 347 slurp, spherical linear interpolation, 352 slicing, 205 soft attributes, 179 soft prompt-based PEFT methods, 336 to 338 sparse models, 68, 427 sparse retrievers, 258 speculative decoding, 428 to 430 spherical linear interpolation, slurp, 352 SQL queries, 277 static batching, 440 static features, 30 stopping condition, 95 structured data, 123, 303 structured outputs, 99 to 104 constrained sampling, 103 fine-tuning, 104 post-processing, 102 index, 507 summing, 350 to 354 linear combination, 350 to 352 pruning redundant task-specific parame ters, 353 spherical linear interpolation, slurp, 352 superficial imitation, 393 supervised fine-tuning, SFT, 78, 80 to 83, 309 supervision, 6 synthesis of data, C data synthesis, system components evaluation, 200 to 201 creating scoring rubrics with examples, 202 defining evaluation criteria, 202 tying evaluation metrics to business metrics, 203 system prompts, 215 to 217 system-level defense, 250 systems evaluation, 159 to 209 evaluation criteria, 160 to 179 cost and latency, 177 to 179 domain-specific capability, 161 to 163 evaluation-driven development, 160 to 161 generation capability, 163 to 172 instruction following capability, 172 to 177 evaluation pipeline design, 200 to 208 step 1, creating an evaluation guideline, 202 to 203 step 2, evaluating all components in a system, 200 to 201 step 3, defining evaluation methods and data, 204 to 208 evaluation driven development, 160 to 161 model selection, 179 to 200 data contamination with public benchmarks, 197 to 200 model build versus buy, 181 to 191 model selection workflow, 179 to 181 navigating public benchmarks, 191 to 197 OpenAI model quality, 196 T task-based evaluation, 201 temperature, 90 to 93 term frequency, TF, 259 text to SQL, 99, 126, 274 throughput, 414 to 415 time between tokens, TBT, 413 time per output token, TPOT, 33, 412 to 414 time to first token, TTFT, 33, 412 to 414 tokenization, 55, 69, 121, 260, 268 defined, 3 tokenizer, 268 tokens, 3, 68 tool use, 296 top K, 94 top P, 94 TPOT, time per output token, 33, 412 to 414 traces, 470 trainable parameters, 320 to 322 training, 41 to 42 training data, 50 to 57 domain-specific models, 56 to 57 multilingual models, 51 to 55 training quantization, 331 to 332 transfer learning, 308 transformer architecture, 58 to 64 attention mechanism, 60 to 62 attention modules, 62 MLP modules, 62 transformer blocks, 62 to 64 attention modules, 62 embedding modules, 63 MLP modules, 62 output layers, 63 truthful QA, 192 TTFT, time to first token, 33, 412 to 414 turn. Based evaluation, 201 U unstructured data, 27, 303 use case evaluation, 29 to 32 usefulness threshold, 33 user feedback, 474 to 492 extracting conversational feedback, 475 to 480 natural language feedback, 476 to 479 other conversational feedback, 479 to 480 feedback design, 480 to 489 when to collect feedback, 481 feedback limitations, 490 to 492 biases, 490 degenerate feedback loops, 491 v-value vector, v, 61 vector database, 261 to 263 vectorization, 438 vocabulary, 123 defined, 3508 index. W. Guido Grande, 192 workflow automation, 28 write actions, 280 Z zero-shot learning, 213 to 215 index, 509. About the author. Chip Huyen is a writer and computer scientist specializing in machine learning, ML, systems. She has worked at NVIDIA, Snorkel AI, founded an AI infrastructure startup, later acquired, and taught ML systems at Stanford University. This book draws on her experience helping major organizations and startups leverage AI for practical solutions. Her 2022 book, Designing Machine Learning Systems, O'Reilly, is an Amazon bestseller in AI and has been translated into over 10 languages. She is also the author of 4 best-selling Vietnamese books, including the series Zac Ba Lo Len Vad, Pack Your Bag and Go. Colophon. The animal on the cover of AI Engineering is an Omani owl, Strix butleri, a so-called earless owl native to Oman, Iran, and the UAE. An owl collected in 1878 was dubbed Strix butleri after its discoverer, ornithologist Colonel Edward Arthur Butler. This bird was commonly known as Hume's owl and it was thought to be widespread throughout the Middle East. In 2013, a previously unknown species of owl was discovered in Oman and given the name Strix omanensis, the Omani owl. No physical specimen was collected, but the owl was described from photographs and sound recordings. Then, in 2015, an analysis of the Strix butleri holotype, the original specimen found in 1878, revealed that the owl was actually the same as Strix omanensis, and distinct from the more common owl found throughout the Middle East. Following naming conventions, the SPECs kept the original name Strix butleri and the more common owl was given the name Strix hatterami, the desert owl. The Omani owl has a pale and dark gray face and orange eyes. Its upperparts are a dark grayish-brown and its underparts are pale gray with narrow dark streaks. It's a medium-sized owl with a round head and no ear tufts. As a relatively new discovery, ornithologists are still researching the owl's behavior, ecology, and distribution. The IUCN conservation status of the Omani owl is data deficient. Many of the animals on O'Reilly covers are endangered, all of them are important to the world. The cover illustration is by Karen Montgomery, based on an antique line engraving from Lydecker's Royal Natural History. The series design is by Edie Friedman, Ellie Valkhausen, and Karen Montgomery. The cover fonts are Gilroy Semibold and Guardian Sans. The text font is Adobe Minion Pro, the heading font is Adobe Myriad Condensed, and the code font is Dalton Mog Ubuntu Mono. Learn from experts. Become one yourself. 60000 plus titles, live events with experts, role-based courses, interactive learning, certification preparation. Try the O'Reilly Learning Platform free for 10 days. Copyright 2025 O'Reilly Media Incorporated. O'Reilly is a registered trademark of O'Reilly Media Incorporated. 718900_7x9, 1875.